Okay, as you guys know, I'm Norm Tubman, and this was work I did largely when I was here as a postdoc at University of Illinois, and we've continued on doing some of this stuff since I've moved to Berkeley. Collaborators on this was Ilkka Kalampa. So most of this stuff actually works in QMCPAC right now. There's some newer functions that aren't quite in the main release. Wave functions, I should say, but you can run solid-state systems and molecular systems with base wave functions to look at non-adiabatic systems. So initial paper was done with Ilkka, and then with Yubo and Jaren, who are collaborators, we implemented a lot of new stuff. So I'm going to show you a little bit about what we've been doing. So when I say non-adiabatic systems, for us this means we want to treat electrons and ions with wave functions simultaneously. So you may know that in most calculations that people have been doing, clamp nuclei calculations, you don't actually treat the nuclei quantum mechanically, but you introduce harmonic and anharmonic effects through various perturbation approaches or frozen phonon approaches or things to that extent. But you can actually treat the protons with a quantum mechanical approach. So this would be the clamp nuclei wave Hamiltonian. And what you can do is you can add the kinetic energy back in for the ions, and you can actually, when you put your wave function down, have coordinates for the ions and treat the full system. This is actually very easy to implement or to set up a calculation in QMCPAC. When you have your particle species, you can have a separate particle species with its own mass, and you can put a wave function term for that species. So hydrogen 2 is something that has no sign problem, and you can just go ahead and calculate it to as much precision as you want. The variance of the wave function will ultimately determine how much computer power you need for what sort of accuracy you want in your problem. Okay, so what type of approaches have people been looking at to go beyond the Born-Oppenheimer approximation and do these non-adiabatic calculations? I'm going to tell you about our QMC approach, but there's actually a lot of different methods that people have been pushing on. So obviously fixed node, we haven't really talked about path integrals in this conference, but that's a way to do finite temperature versions of non-adiabatic simulations. I'm going to tell you in the next few slides a little bit about correlated basis sets. And this is sort of it's a largely neglected field, I would say, in quantum chemistry, or not widely used because of its limitations in going to large system sizes. But for the systems it can do, it's really accurate. And I'll show you what I mean by that in a minute. And then there's a lot of chemists who have been working on beyond Born-Oppenheimer approaches. Sharon Hamish-Schiffer here has been working on NEO methods, and there's all different types. And she's also been working on multi-component density functional theory. And there's been a lot of progress with these techniques, but ultimately it's not clear how to really get to higher accuracy and higher or larger system sizes with these, whereas we think we can make some progress with fixed node diffusion Monte Carlo. I want to give you one slide overview on what these explicitly correlated basis sets look like. So the one thing I'm always benchmarking against is something called explicitly correlated Gaussians. And this is literally one element of an explicitly correlated Gaussian basis. And you can see it's got coordinates of all the electrons being subtracted and added with each other. So it's explicitly correlated. We're not building up a wave function from a single particle basis set. And then you take a bunch of these, you sum them together and optimize all your parameters. They actually use Monte Carlo in some cases to optimize their parameters. And you explicitly anti-symmetrize these things. And that should tell you why these methods take a long time. If you anti-symmetrize single particle orbitals, you can do that in a determinant, no problem. This isn't a determinant. To explicitly anti-symmetrize other functions, it's going to take you factorial time, and that's why these methods really have a hard time scaling up. But you get benefits from trying these sorts of things. So I like to take outsiders' points of view on what they think about quantum Monte Carlo and other techniques. So I introduced explicitly correlated Gaussians on the previous slide, and this is a page or a table from a review of modern physics of explicitly correlated Gaussians that came out in 2013. So they have 5 different methods here and a bunch of different types of systems that they want to consider. Obviously, everything, probably most of the stuff we consider here just gets one line at the end, more than 6 atoms. So that should tell you roughly how big they think their methods can work. The CI and the QMC are familiar to you guys. I introduced ECG on the previous slide, and you should take the Hilarious and the hyperspherical as also to be correlated basis set methods. Now, this is kind of an interesting chart. We're just going to ignore most everything just for the next few slides, except this first row here, atomic systems for n less than 3. And I have the sentence here, it's important to use the right method for the right problem. And that's to say, quantum Monte Carlo is exact for a lot of n equal 2 systems. But that doesn't mean you should actually use it for various reasons I'm about to show you. And one of these things is, if you look at this line, QMC is considered good for n equals 2. It's exact, but it's only considered good on this chart. ECG is considered high precision, and Hilarious is considered extreme precision. So what does that mean? So this was an example from Chen and Anderson. This is the diffusion Monte Carlo calculation in 1995. It's the H2 molecule, which I just mentioned previously. I didn't say a lot about it in the previous slides, but there's 2 electrons, spin up and spin down. There's 2 protons, 1 spin up, 1 spin down. There's no sign problem because nothing is antisymmetric. Well, it has to be explicitly antisymmetrized with each other because they're all unique particles. They wrote down a explicitly correlated basis set, or I said in terms of relative coordinates. So this is the DMC wave function, or VMC wave function they use. They optimize these parameters. Everything is relative, so things can rotate and translate as they need to. And they were able to get this answer, which looks really good, about 7 digits of accuracy. So, and that's exact. It's not biased within the error bar. But if you do ECG, which is a basis set method, explicitly correlated, but still a basis set, it's biased, but you get 10 digits of accuracy. And that's kind of nice. And how do they know they have that sort of level of accuracy? This was a paper that they did in 1999. So they have Anderson and Chen's number here, and they say that H mass is not given. So if you only want this many digits of accuracy, the mass, or how many digits you use in the mass, probably isn't that important. But as people started to do more accurate, explicitly correlated type Gaussian calculations, they started including many more digits in the mass, because then it becomes an important issue. But the main way they know that they're converging is they have a basis set parameter, and they can increase that and see how many digits, how the digits change as they go from 7,000 explicitly correlated Gaussians to 10,000. And they get an error of roughly 10 to the minus 10 or 10 to the minus 11 AU. And they can just go ahead and do excited states also in the same sort of method. So these are things that quantum Monte Carlo isn't particularly good at, getting all these digits, doing all the excited states, and these ECG methods can. But a funny thing about this is, for a long time, no one used explicitly correlated Gaussians, or not very many people. So in this review of modern physics I mentioned, they would say that until the 1990s and 2000s, really, this is a citation of the main ECG papers that came out in the 60s, I guess. No one really used these techniques. And they would say the reason why is that the Hilarious method is even much better than the ECG method. So there's a paper, mid-2000s, by Charles Schwartz. And he was looking at the helium atom. So this is 2 quantum particles. And if you look in the abstract, you'll see that there's 45, 46 digits of accuracy for the helium atom with the Hilarious method, which is, I guess, 30 more digits than what the ECG method can do. And you'll look, they even have 3 dots here, so there's more digits that they aren't reporting. If you look in the paper, they actually give you 2 more digits, so that's a bonus. And that's sort of how it goes for these smaller systems. So in this review of modern physics, they start looking at various atomic systems. And you'll see diffusion Monte Carlo, so this is for the helium atom. You'll see diffusion Monte Carlo doesn't make the list. It's not competitive with a lot of these explicitly correlated Gaussian, or explicitly correlated basis sets calculations. So ECG is up here. It's about 10 to 15 digits, but the Hilarious is about 45. And then they start going down the list of various other atoms that they're interested in. So you'll see lithium up top. There's the CI, which isn't very competitive with the ECG, which isn't competitive with the Hilarious. and then you keep going down, increase the number of quantum particles. Eventually, Hilarius is gone because now we have more than 3 particles, and it's really hard to do these calculations with a Hilarius basis set beyond 3 particles. But ECG is still in the game. And CI, this is a very accurate calculation, not quite as accurate. You'll see, even though they report the same number of digits, the last few aren't as accurate as the ECG. But then you keep going down. At some point, you get the DMC energies coming in. They're still, by carbon plus atom, not quite as accurate, but that's sort of where things stop. ECG methods, all these explicitly correlated methods are essentially exponentially scaling. And where they stop at C+, so this is a paper from Paul Yang in 2016. He was just able to keep going, C, nitrogen, oxygen, fluorine, and other people have done it before also, and it's not really a problem for diffusion Monte Carlo. So as I said, the right methods for the right problems, if you really have very few number of particles, quantum Monte Carlo may be exact in some of these cases, but it still may not be competitive with other methods in terms of accuracy. And here's another example. This is full non-adiabatic, so electrons and ions treated as quantum particles with the ECG method. These are various citations and the energies that people have gotten for these various molecules. You should take as going from top to bottom. You're increasing the number of quantum particles in the system. And you can see every particle you introduce, you literally lose an order of magnitude of accuracy down to when you get to boron hydride, in which they really only have millihartree accuracy for their energy. So let's talk a little bit about QMC and what's been done. So these are David's, these are really some of the first papers, even before the molecular stuff. There must be a couple older molecular papers, but before the Ben and Chen, David was looking at this for hydrogen systems. People started looking a little bit at non-adiabatic systems in 1995 and onwards with quantum Monte Carlo, but because of the sign problem, the accuracy isn't there beyond the H2 molecule or helium atom for a lot of these calculations people want to do. So I showed previously, this was the wave function that Ben and Chen used, and because it's a molecule and only 2 atoms, they really could get away with writing down everything in relative coordinates and expect to have a decent wave function with low variance. For the solid-state hydrogen calculations, they used Jastrow-like parameters between the electrons and the ions. They used determinants for the ions, and then they used a proton product of Gaussian orbitals strictly for the ions. So they had lattices they were interested in looking at, and they'd put down proton wave functions or orbitals around each lattice site. And they were able to get some really nice energies out of this. Because this is kind of a quick talk, I'm not going to tell you we have a lot of new wave functions we've been testing. Some of it's in QMCPAC proper, some of it's on the side right now, and we'll eventually factor it in. But we have been able to really address some of the sign problem issues by making much better wave functions for molecular systems. So to begin with, I'll just show you lithium hydride really quickly. The only thing I want to emphasize on this slide is this was our best infinite basis set QMC answer. And for a long time, we were comparing to experiment. And we were really we weren't upset with it. It was like 1 millihartree accurate in comparison between them. But we felt we should be able to do better. And eventually we realized there's an ECG result that was an order of magnitude closer to our value. And we actually think we're right, and the experiment is a little bit off. And this is something that we begin realizing. There's some experimental values that disagree with us, and we're not always sure if it's us or if it's them. But in this case, there was a thermodynamic benchmarking done by David Feller. A few years before that, we also found that also more agree with our results. So we're somewhat confident. Also, I should say, these ECG results are really converged to this many digits of accuracy. So it seems unlikely any other method that I can think of right now will be able to get much lower energy. So we are pretty confident about our results on the lithium hydride. But as I said, we can just go and scale up, do more electrons, more systems. So all of this is from Paul's paper back in last year. And the ECG results for these systems we consider to be nearly exact, at least on the 10 to the minus 5 Hartree scale. And you can see that we're roughly spot on for the lower number of electrons and ion elements. And we lose a little accuracy as we go to boron and carbon, but we're still roughly 0.1 millihartree accurate. It's almost as much as we want. So I should say there are a lot of applications for what we're doing. One of the things I'm somewhat interested in is diffused interstellar bands, identifying molecules out in outer space through spectroscopy. And we actually need more accuracy in excited states to really start identifying molecules. So this all looks good, but it's not quite there yet. We have to do some more development. But at least we look to be very good and accurate and getting in the right direction. And I should also say, these results right here are unusual. So the blue is clamped ions and how accurate we are compared to ECG, and the red is the non-adiabatic. For some systems, our non-adiabatic calculations are more accurate than our fixed ions. And I can't explain it. It doesn't seem like that should happen, but it certainly seems to be the case for some systems. Now we're going to go to, we also did molecular systems in this paper. And this is also a comparison to the ECG results. And for lithium hydride, you can see there's a slight bias, less than maybe 0.2 or 0.1 millihartree. But then beryllium hydride, we're really getting right where the error bar in the ECG results matches our result. And then for boron hydride, they have a huge error bar. All of our results are variational. So we definitely know the energy is at least down here. But beyond that, ECG results don't exist, and we're really the only game in town. So we started looking at some of the heavier, or more of the first row hydrides. And this is a comparison of experiment. So this is atomization energies. So these are, if you don't include harmonic, antiharmonic, non-adiabatic effects, these are just the clamp nuclei results. If you include harmonic corrections, then you get the green results, and the red results are full non-adiabatic simulations. And you can see for most of these, experiment really isn't helping us to see if we're actually improving our accuracy or not. The error bar in lithium hydride is kind of large. We think the results in beryllium hydride aren't quite right, and ECG results agree with us and not them. For boron hydride, the error bar is incredibly large. And for carbon hydride, that's kind of an interesting case for us. It's the only case where we see a huge difference, relatively huge difference, between adiabatic and non-adiabatic simulations. And if we look at a decomposition of our energies, so we can do calculations of the clamp nuclei, we can calculate diagonal Born-Oppenheimer effects, we can calculate harmonic effects, and we can partition out the energies into these various components. And if we just take the last two smallest ones, which one is the diagonal Born-Oppenheimer correction, and the remaining we consider to be the pure non-adiabatic energy, for carbon hydride it's actually quite large compared to the other molecules we're looking at. This disagrees with the experimental results. We're not quite sure what's going on. We've spent some more time looking at better wave functions, and this reduces a little bit, but it's still quite large. But this is something that we're interested in exploring more. So to extend that last point, I think there's many possibilities for improving wave functions and running larger systems with fixed node diffusion Monte Carlo. Paul's been testing, as of this week, even non-adiabatic simulations of high pressure hydrogen, so we're hopefully pushing on that and getting nice results. In terms of other methods that you might consider instead of this, it's not clear to me for solid state that there's really much competition except for path integrals. And for molecules to go beyond 6 particles, most of these other methods are very approximate, don't include correlations, or they just don't get very good results. And I don't mean to make that in a broad umbrella. There's some very nice methods and work out there, but things that can systematically be applied to a lot of systems. I think fixed node diffusion Monte Carlo is one of the only games in town right now. So with that, That's the end. You can see our papers on this. Paul's paper is here, and we recently submitted another paper where we've improved the wave functions further. I didn't really give you any of the technical details of how we improved the wave functions, but they're all in these papers, and if you're interested, you can check it out. Thank you.